Okay, so I hope everyone's still surviving after 5 talks and you're struggling to get towards the coffee and croissants out there. I'll make this talk nice and simple. I hope that I'm going to be talking to you about something that you're already convinced of, the reproducibility of your science. So my name's Gavin Brown. I am Professor of Machine Learning at the University of Manchester, and this is joint work with a few other people, including Kostas Sakidis, who's now at Roche there, and some others from AstraZeneca a couple of years ago. But I'll go into the details. So reproducibility is kind of a big deal. A lot of people in their respective fields are experiencing issues with papers being retracted many years later based on key results. Just a few days ago, a Nobel Prize winner retracted one of her papers, not the Nobel Prize result, live on Twitter, I think it was the 3rd of January. And it's happening in every field of science, not just your particular one, my particular one. So if I start the talk with a little bit of interactivity, can I ask to check if your elbow is working, and raise your hand if you've ever had an issue in reproducing an experiment in your field, maybe someone else's result. Yeah, I should probably take a photo of this, but it's pretty much everyone. So let's try this again. Would you say in your respective field, there is what you would call a crisis of reproducibility? 1, 2, 3, 4, 5. Okay, so about a quarter of the audience. So Nature asked this question, and half the people in their survey said that there is pretty much a significant crisis. Only 10% thought that there was not some form of crisis in their field. It's a pretty big issue for science if you can't reproduce your experiments. So of course, as machine learning and data scientists, this is the sort of operation we're used to. We're not really, some of us are, we're not really wet scientists. We're not messing around with test tubes and so much, perhaps, but we're dealing with data. So let's imagine, I want you to imagine this is your data science pipeline. You start from some big form of data in some database somewhere, you do some operations, and out the end come some small data. You've processed it in some way. And based on that small data, you'll make some predictions, you'll make some conclusions about how you'll do some investments within your company, or who you'll give the drugs to, or these sort of things, right? But what happens when your data changes? If your data were to change, you imagine an alternative universe where some of your original data, maybe just 1% of your data had changed. Would you still have come out with the same conclusions? And what this really gets to is the set of operations you're performing in your pipeline uncovering a robust hypothesis in the data? Is it a reproducible hypothesis? Is it trustworthy? But of course, this is not what most people's data science pipelines look like. Most look like this. You might have multiple tools. You might have, you might have people in the loop. If you're one of the cool kids, you'll have a neural network in there, or even cooler, you'll have a Bayesian neural network in there. And I'm not saying that to be insulting in any sense to the previous speaker, but there are a lot of very great efforts to increase the reliability of said tools, and Bayesian neural networks are indeed more stable, in my opinion, than traditional neural networks. But this still doesn't detract from the fact that there are fragile operations in all of our data science pipelines. So you'll notice I've been using this word trustworthy and reproducibility kind of interchangeably. And this is a conclusion that I've come to after thinking about this for a while, that reproducibility is trust and vice versa. You don't trust or not trust something. You trust something to a degree. You might trust different components of an organization. You don't just trust the organization yes or no. So as a result, reproducibility is not really a yes-no question. It's something that you may be able to think about in degrees. So I'll give you a conjecture that we can measure, or should at least try to measure, reproducibility. And this is what this talk is going to be about. So let's take a very, very specific example of reproducibility, or at least a challenge for reproducibility. We're going to talk about data-driven biomarker selection. So let's say we have some problem that we want to make some predictions for. We have a lot of genetic observation, a lot of genetic measurements from someone or some other clinical measurements on a huge number of those and a very small number of patients in our particular cohort. And we have some phenotype that we want to be able to predict. Now, only a subset of these will in fact influence the phenotype, and we want to find those marked by the red crosses. If we attack this with traditional data science methods, this is what's called a feature selection problem. I'm sure all of you have at least heard of this, if not used these tools yourself. You'll start from this body of data. You'll apply some feature selection algorithm, your favorite one, whatever it will be, think of anything. And maybe just to be extra sure about the way it's going to be working, you'll try different ones. Out the end of this will come a set of features, saying these are the important ones. And then just to be extra sure that you've got this right, you'll do some form of cross-validation in the middle of the operations here, just to be extra sure that these 5 features are the ones that you want to be concerned with. But then, let's think what would happen if we were to drop a random 1% of the original data. Just imagine that a couple of patients didn't turn up to the clinic that day to get measured. Maybe one of those markers would have changed. Maybe it doesn't come out as significant anymore. Maybe 2 of them change. Maybe there's some variation in this final set of chosen features. I'm going to refer to this variation as stability. And stability is a specific instance of reproducibility in a data science pipeline. Then there are others. So let's think how we could measure this. We're starting with our features, and we've identified that these marked 5 ones are the ones that we want to say, these are the important ones. And so these are in our bag. We say these are the important ones. And then, of course, some are out. So immediately we're thinking set theoretic operations. There are some in the set, some out of the set. And if we have this, we look at this dropping 1% of data. If we start with all data, we have this set. If we vary by dropping a couple of percent of the data, maybe we'll get the bottom set there. So we could look at, say, the set intersection between these two sets of features. And then we get into the question, well, okay, we could consider things other than just the set intersection. And set theory, I'm pretty sure you've all heard of it, it is kind of a discipline that's 200 years old, and it's thought of quite a bit. And so there are lots of measures of set theoretic operations, lots of ways to normalize things, taking a normalization by a geometric mean or a size of a set or a size of a union, and lots of other operations. And there's not really a principled way to pick, what are we going to use as our measure of similarity between 2 subsets chosen by the procedure when we vary that 1%. So let's think from a more principled perspective. What we're going to do is name a few properties and axioms that we want to hold for this particular stability problem. So we're going to pick a few properties, we're going to name them, and then we're going to see where do they point? Where do they imply we should be looking within the body of literature for the right measure? I'm going to tell you about a few, a few of them today. I'll tell you where to find the rest if you want to do some more reading. The simplest one, which I hope everyone might agree with, is if we're going to have some measure of similarity, it's got to have something to do with intersection in some form. If there are more features in common between 2 runs of an algorithm, then probably there is some correlation between those algorithms. So as the subsets begin to overlap more and more, the set measure should rise in some sense. I'm not saying at what rate or where it should plateau or anything like this, but it should rise in some sense. Another property that we might want. We want to know what are the upper and lower bounds of this measure. We don't want a possible outcome of the measure to be infinity or negative infinity, primarily because this means we won't be able to compare outcomes across experiments. If my outcome is plus infinity and yours is plus infinity, well, what does that really imply? There are different degrees of infinity, as we know, so it kind of confuses the matter. So what this implies, to some degree, is that we're going to avoid logarithms. These tend to give infinities when you mess with things. This is not a strict rule, but it does give some guidance as to what's coming. Finally, the last one I want to talk about is if you are selecting, let's say you have a bag of features, of 200 features, and I pick 2 of them randomly, and you pick 2 of them randomly. The chances of us picking the same pair of features is pretty slim. But if we have a bag of 5 features, the chances of us picking the same pair from that smaller bag is kind of much, much higher. So you have to normalize for the overall pool size, called a correction for chance, as we refer to in the paper. So with all these properties, you'll remember this huge list of set theory measures that I discussed. And you could pick any one of them from 1957 up to 2016 or 17, whatever you want. And what we did is ask ourselves which properties hold for which measures. And we did a nice table. And if you really want to look at the 75 proofs that we had to do, or rather my PhD student Sarah had to do, thank you Sarah if you're watching on YouTube, 15 measures times 5 potential properties, 75 proofs. So we looked through all the literature, and drum roll, this was the outcome. So these are actually ordered chronologically. So way back in time, there were some measures that had lots of properties, but a critical one missing was this correction for chance. Around 2007 or so, which is that Kuncheva paper in the middle of the table, this was corrected, but it turns out to lose certain other properties. And these properties were kind of, missing in different parts of the literature. So what this led us to believe is that given this, we need to modify one of the existing measures to give it back these correction for chance or design a new one. So we asked ourselves, where does this point? And so this is the one and only equation I'll show in the entire talk. And it's just really a jaunty angle to distract you from the algebra. But really, this is just a modification. There's a covariance between Bernoulli variables normalized such that you get this correction for chance. And it turns out that there's a really nice closed form solution as the trace of a product of 2 matrices. And this turns out to be very easy to compute, so you don't have quadratic operations in the number of trials you want to perform, but just closed form, one pass through the data, very easy to compute. And it turns out to give lots of neat statistical properties, such as it comes with confidence intervals for free, all sorts of other things that are available in the paper if you'd like to have a look. The slides will be available online after the talk, I believe. So now we come to actually applying this thing and seeing whether this tells us anything. Does reproducibility tell us anything about our experiments? So we did a piece of work with our colleagues at AstraZeneca, and they were looking for prognostic markers that had some kind of indication for recovery in non-small cell lung cancer. So we did some operations on the data. And we were testing 2 algorithms, GBM, that's the gradient boosting algorithm that was referred to earlier, and CMIM, that's a mutual information-based algorithm. And the 2 procedures, the boosting one came up with this set of features, and the mutual information one came up with this set of features. And in terms of predictive accuracy, these were pretty much identical, no way to distinguish them. In terms of a biological hypothesis behind what had come out, I'm not the biology expert, but my colleagues told me that there were plausible explanations behind both of these sets as to which ones could be causative in this factor. So we thought, okay, how can we distinguish between these two algorithms for the way they're moving forward? And this is where we came back to reproducibility. If we were to drop small portions of the original data, like 1 or 2 patients, if one of these has locked on to a causative relation, a stable biological mechanism, it will be more stable with respect to perturbations in the data, more reproducible. So if we look at the top row here, this gives the stability of the two algorithms. The GBM one, dropping quite large portions of the data, came out as 0.87, where the upper bound is known to be 1, stable. So highly reproducible. And this mutual information-based one came out as quite a lot lower, not very reproducible with respect to perturbations in the data. But then we started going further, digging into the data. And one of the abilities that the measure we've designed gives us is to incorporate biological hypotheses into to kind of group features, similar to group lasso. If you know of these techniques, you can kind of say, right, these features are very similar to each other, disregard any variability between them. So we looked and we found that several of the genes that we were considering were to do with EGFR in some form, and that's known to be associated. And so we thought, okay, we'll put those in a bag and we'll say any selection, any variation within that pool, we won't look at because it's kind of picking something from that area. And what that tells us is the reverse. So the GBM method stayed pretty much the same, quite reproducible. The CMIM method, now we incorporate this biological knowledge that, okay, anything within this pool, you can discount variation because it's locking onto some hypothesis in that area. It came out as much more stable. So it changed our view about which is the most reproducible hypothesis in some sense. So this was one of a number of experiments. As I said, the paper is available if you wish to have a look. But my take-home message is really quite simple, that reproducibility is not a yes-no question. It's not that this research is reproducible and is good and this one isn't and should be retracted. But it is a degree, and we should come up with ways of measuring it, quantifying it, and discussing it between studies. Okay, thank you. Yeah, gentleman back there. Yeah, so are there studies to include the feature correlations in the stability? Yes. Yeah, so that's exactly what we were doing here. We were encoding either measured correlations or known dependencies into, if I go back into this matrix, so there's a matrix C up there, and you can just look, that's a covariance matrix, or you can populate it with ones, and you can just build in your biological knowledge there into correlations. Yes?
I mean, it's a very nice work. I wonder, it seems to be a very easy exercise to make algorithm absolutely stable. You just select features based on their name, alphabetically sorted, or based on the mean value. I'm wondering, like, how do you distinguish this the stability because of some tricks versus stability which really brings something to the model?
So this is a common question that I've had when talking about this sort of thing, in that people think we are trying to make the algorithm more stable. Really, this should be thought about as a measure that you can take post hoc after you've already decided, right, these are the sets of features that we consider the best. We've done everything we can. This gives us a high accuracy, or it's got high biological plausibility. Now let's check the reproducibility. It shouldn't be incorporated into the pipeline so as to make it more reproducible without sacrificing, if you're going to sacrifice your accuracy or your biological plausibility for reproducibility, then that's a bad thing. So it's something that comes at the end of an investigation. Once I've got two hypotheses which are indistinguishable, which one's more reproducible?
So maybe last question here, and we have
Sorry, the question I was wondering the following. And when you use, for example, neural networks, people tend to throw 500 features a day, and then they kind of let it run through because they hope that the feature engineering part will actually do the work for them, kind of, right? So I was wondering, is in a sense you could actually link this work to also to the interpretability of those models, because you could start taking out features and see if the network would work as well as before. At a certain point you would notice maybe some are important, some are not important, and you could actually link it to kind of, I don't know if it's something that...
Yeah, so if you're asking, are features in a neural network important or not important, there are actually already methods to do that, automatic relevance determination and so on. These are techniques that have been around for a long time. But this isn't really about a process to discover the most important features.
If you change the architecture of the network, maybe some other features would be important for the same problem. So the question is...
Exactly, yeah. From this perspective, one could say we've used a neural network to come out with this conclusion. So now let's have small variations in the architecture of the network and see, is my conclusion stable with respect to those small variations? The trouble, of course, is just to train one network usually takes a week's worth of compute time at the moment. So it's compute intensive, but feature selection is an operation that's quite fast these days. But yeah. Okay, thanks.